This is your friendly neighborhood physicist, Dr. Doherty, here with part 2 of the rotational videos. So last time we talked about rotational kinematics. How do things like angular velocity and angular acceleration work? We took our basic variables, x, v, and a, rewrote them as theta, omega, and alpha. Just did stuff in Greek so it looked fancier. This video is going to look at things like force, energy, and momentum, and how we apply these to rotating objects. So the first thing to think about is force. If I want to make something spin, I need to push it somehow, but it also matters where I push it and the direction of my push relative to the object. So if we do some experiments, we can figure out that the torque, tau, depends on force times the distance between the force and the axis of rotation times sine theta. Let's kind of break these down one at a time. I want to make something spin. Go to a door in your house somewhere. So the harder I push the door, the faster it spins. That's turn around its hinges to open or close. The further away I push from the hinges, the easier it is to turn. So if I want to push right near the hinges, it's really hard to open a door. If I push on the outer edge, where the doorknob is, the door is really easy to open. Now last thing is theta. Theta is going to be the angle between my force and the object. Now normally we'll put theta to 90 degrees. If I want to open a door, I push perpendicular to the door. Your body understands torque. You just got to get your brain to do it. Now sine of 90 degrees is 1. So that sine theta term will go away lots of the time. But if the problem is mean and they give you a funky angle, just throw that in. Now, we have an important distinction to make for directions, just like last time. So we defined omega to be positive when something's rotating counterclockwise. Same thing for torque. If my torque is going to make an object spin counterclockwise, it's a positive torque. If it makes it spin clockwise, it's a negative torque. Don't forget that. It's really important. As always, your life is easy if you remember units. Torque is Newton meters, so I got to have force times distance. When we first started talking about Newton's laws, we had the law of inertia, and we had the second law, F equals ma. Now, the law of inertia says that if there's no forces acting on an object, it's not accelerating. And by the definition of acceleration, that means its velocity isn't changing. So an object at rest tends to stay in rest. So when we did these problems, what we did is we said, if the acceleration was 0, either in the x or y direction, then the net force must be 0 in x or y, because force causes accelerations. No acceleration means no force. What about the rotational world? Now, if my alpha is 0, the angular acceleration isn't changing. That must mean that the net torque is 0. So these equilibrium problems are just like before. Instead of saying 0 net force means 0 acceleration, I'm going to say 0 net torque means 0 angular acceleration. So a simple idea to help us get started here. Let's think about a balance scale. So imagine something that you would use to measure in chemistry lab, or the things that the blind justice statue lady is holding in her hands. So I've got two arms here, D1 and D2. Let's set them both equal to each other, say 20 centimeters. I'm going to hang 50 Newton force off the left. How big does the force on the right need to be to balance? Well, okay, I don't need fancy physics to say F2 has got to be equal to F1. Let's think about the equation, though, for a second. All right, so I'm going to do my net torque is equal to 0. So I'm going to have an equilibrium situation. I'm hanging things in balance. It's not turning anymore. So let's talk about what my torques are. So I'm going to have two. I'm going to have one from force 1 and one from force 2. Now force 1 is going to make this left side go down, which makes the right side go up. So this arm here is going to rotate this way. This direction, moving my mouse up here, is going to be counterclockwise. So that's right, this torque is going to be positive. So this torque on the left is going to be force times distance. Now because these are perpendicular, theta is 90 degrees. Sine of 90 degrees is 1, so I'm going to ignore the sine theta bit. Okay, now on the right, my force 2 makes it go the other way. It's going to make this right side go down, which makes the arm rotate this way. That's the clockwise direction, so my second torque is negative. So when I write this down, my first torque is going to be F1 d1. Again, sine theta is 1, so I'm skipping it. Positive. Minus my clockwise torque, F2 d2, and these things are going to be equal to 0. Okay, in my problem now, I was given d1 and d2 and f1, solving for f2. So I do a little bit of algebra, f2. This is going to be what I call the lever equation. It's going to explain how levers work. The amount of force I need to balance depends on d1 and d2, and if they're not equal, f2 could be a lot different from f1, and everything could still be perfectly balanced. So, more extreme example. If d1 is 200 centimeters and d2 is 10, now my balance scale looks like this. If I hang 50 newtons off the left, how much do I need on the right? Well, I have the same torques in the same equation. So copying and pasting from the last time and solving for F2, I now get 1,000 newtons. I can use torques and levers to turn a 50 newton force into a 1,000 newton force. This is why levers are a powerful, powerful thing. All right, one last important idea for equilibrium. If I've got an object that's not rotating, so the alpha is 0, the net torque is 0, it's just sitting there perfectly at rest, what's the axis of rotation? Sometimes it's not really obvious. If it's not rotating, where do I put the axis? Well, the cool thing is we can put it anywhere we want. So what that means in a practical sense is I can make my problem easier by putting the axis of rotation somewhere. So if you're going to have a problem where there's 2 or more torques acting on an object, but you don't know everything. So let's say I've got 3 forces that are acting on something, but 2 of them are unknown. Well, no problem. All I got to do is put the axis right on top of one of my unknown forces. Then the torque from that unknown force is going to be F times d, and d is 0. So when I put the axis there, that torque becomes 0. My problem becomes much, much easier. Last important thing when we're dealing with these torque problems. If I've got an object, I need to act as though its entire weight force is acting solely at the center of gravity. It doesn't matter how big the object is, how weird it is, if it's resting on stuff or balancing on things, I can put the entire force as though it's at the center of gravity. That makes problems a lot easier. So if I'm finding the torque about this rod, I put the whole weight, the W equals mg, right here at the middle. And if I've got this butternut squash looking thing, I put the whole weight at its center of gravity right over here. If you've got a simple object, center of gravity is at the middle. If you've got a more complicated object, the center of gravity, you have to take a weighted average of all the weights to find it. Now this is really important to us when I'm talking about objects and stability. So if I've got an object that's sort of resting on the ground somehow with some supports, so like I'm standing and my 2 feet are on the ground, my 2 feet are keeping me up. As long as my center of gravity stays in between my feet, I'm balanced. If my center of gravity, though, moves past that, I'm going to have torque, and my net torque is not going to be 0. So let's look at this cargo plane here. So how do you get a FedEx jet to pop a wheelie? Well, if the jet is balanced, the center of gravity is here in the middle, in between the 2 wheels. So if I put my axis of rotation here on the back wheels, I get a downward force giving me a negative torque from the weight, but I get a upward force giving me a positive torque from the normal force on these front wheels. This can be imbalanced. Everything works out. But if I put too much heavy stuff in the back and too much light stuff in the front, my center of gravity moves back here, and because the entire weight vector axis there, I got my axis of rotation. Now my center of gravity is going to be a counterclockwise torque. The normal force is counterclockwise torque. Now my net torque's not 0 and my plane is going to do this. Really fun, Really bad for business. Another simple example of why torques matter. Let's think about things like a Humvee repurposed for military use. Why does it look the way that it does? Why is it so short and wide? The center of mass needs to be between my two tires for it to be stable. Once I tilt it, if my center of mass gets past one of these wheels, now there's going to be a net torque making this thing flip over. This is why SUVs that are tall and heavy can be unstable and flip. But if my SUV is short and squat and wide, it can tilt at extreme angles without flipping over. Other things that are really good at this, sumo wrestlers. This is why they stand the way that they do. So if I have non-equilibrium, if there's a net torque that's not zero, now I got to do the angular version of F equals ma. So before, if I said there was a net force, its acceleration I could find easily as F divided by m. So if I take this equation, I multiply and divide by some factors of r to turn my F into torque and an a into alpha, I get this thing. Tau equals mr squared times alpha. So I'm going to rewrite this now as my net torque equals I alpha. This is the angular version of F equals ma. So we talked about a Rosetta Stone last time. All my x's become thetas, all my v's become omegas, all my f's become taus, all my a's become alphas, and a new one now. All my m's become i's. So my net torque is my angular mass times my angular acceleration. All right, what is this I thing? I depends not only on how heavy something is, so I've got its mass in kilograms here, but also how far away is that mass from the axis of rotation. You know, if you pick up an object and you try to spin it, what matters is not just how heavy it is, but is that mass far away from where I'm trying to spin it or not? And which axis I'm trying to turn something on can make a big difference on how hard it is to turn. Now, if I do my angular acceleration in radians per second squared, and my I in the right units, I get my torque in the right units as well. So let's look at this I thing. Now, if I have a rotating shape, like I've got a sphere or a hoop or a disc or a rod, go online or go to a table like this one and just look up the values of I. There's a Wikipedia page called List of Moments of Inertia that you can just bookmark if you want. Or just ask Google or Siri or Alexa or your favorite robotic assistant to find it for you. Now, if you really enjoy Calculus 3 and you have some free time on your hands, you can calculate this. It's not so hard sometimes, but it's not a lot of fun. Do what I do, look it up. Everything here has units of kilogram meters squared. But what changes is this coefficient out in front. So if I'm going to spin a hoop, I is mr squared. It's got a fair amount of angular mass. It's hard to turn. But something like a solid sphere, I is only 2/5 mr squared. It's a lot easier to turn. If I take a rod and I turn it about the middle, I is 1/12 ml squared. It is 4 times harder to turn it about the end when I is 1/3 ml squared than about the middle. So remember, I is our rotational mass. It depends on mass and how far away from the axis the mass is. Cool example of this. Suppose I want to maximize my inertia. I want to be rock steady, impossible to knock down or tip over with an object I can carry really easily. Well, I would want the I to be as big as humanly possible. I want to have all the mass be as far away from me as I can, but still have the object be really lightweight and portable. Well, what I'd use is one of these. You see, this is why tightrope walkers carry a long pole. That pole increases their I by a lot. So a little bit of torque from them wobbling so that their center of gravity is not over the tightrope anymore means that their alpha is going to be smaller, so it takes them a longer time to fall off and they can fix it. All right, so that's the idea of Newton's second law tau equals I alpha. Let's do two last ideas and call it a day. We've seen how work changes kinetic energy. Let's do this in angular variables. Okay, so we can calculate kinetic energy, do the transformations, and I get kinetic energy is 1/2 I omega squared. Now if I just take my old kinetic energy, I turn my m into I, my v into omega, the equation just works, still has units of joules, don't have to think about it anymore. Now this is going to be another term in our conservation of energy equation. So far what we've talked about is gravitational potential, mgh, translational kinetic, 1/2 mv squared, and now I have rotational kinetic, 1/2 I omega squared. So if I'm going to say calculate the speed of a block or a hoop or a disc after it rolls down a ramp, I've got to throw in this term, 1/2 I omega squared, if it's spinning. Okay, what about momentum? We had P equals mv, so my mass becomes an I, my v becomes omega, and I'm done. Normally, angular momentum is called capital L. Sorry, it's not a Greek letter, it's just what most people do. So angular momentum is L equals I omega. Now this one has different units than normal angular momentum. That was kilogram meters per second. Now I've got kilogram meters squared per second, so I've got to pay attention to that different unit. But the idea is exactly the same as before. So when I did normal linear conservation of momentum, what I would do is I would have two objects and one would crash into the other one, and I'd say the momentum before the collision and the momentum after were just the same. So I add up all the mv's before, add up all the mv's after, set them equal to each other, and I'm done. For a conservation of angular momentum problem, same idea, slightly different execution. In these problems, I'm going to have an object that's spinning somehow. So my initial L is going to be my final L, as long as there's no weird external torques acting on my system. Then in my problem now, some object is sitting by itself spinning, there's no other torques acting on it, and then something changes. Now, since L is I omega, L initial equals L final means I omega initial equals I omega final. So maybe something happens to change an object's I. Maybe it gets heavier or lighter. Maybe it changes from one shape to another shape. Maybe an object kind of moves around it. So if I've got like a merry-go-round, maybe one of the riders moves from one point to another point. If my I changes, my omega has to change. That's all we're trying to say. So these problems are really easy to spot and not too hard to solve. One last note before I move on. If I have a point mass where I is mr squared and omega is Vr, this equation becomes RV initial equals RV final. That can be real help sometimes. So what do I mean by angular momentum being conserved? So I take an ice skater, she's spinning around. Her initial L is I omega. When she brings her arms in, her mass is closer to the axis of rotation. So what's going to happen is her I is going to become smaller, so her omega is going to become bigger. Conservation of angular momentum means she speeds up when her arms go in, she slows down when her arms go out. Okay, what about a slightly bigger example? Here's a picture of our solar system. All of the planets are orbiting in almost exactly the same plane and in the exact same direction. Now, why is that? Well, whatever created the solar system, some kind of giant rotating gas cloud, had angular momentum. So when that kind of condensed and collapsed into planets, that angular momentum was conserved. So the angular momentum of my solar system now has to be the same as it was before. So if my angular momentum of my solar system was rotating counterclockwise from this point of view, everything now is going to be rotating counterclockwise from this point of view as well. Small scale. All right, we can do this. Here's a picture showing the arrangement of electrons outside of a hydrogen atom as a function of angular momentum. So as I increase angular momentum, either by going across or by going down, my electrons go from being very close to the nucleus in the middle to being very far away from the nucleus on the outside. More angular momentum means they behave differently. One reason this thing is so important is because 3 of the 4 quantum numbers are based on angular momentum. The 4th one, of course, is energy. So if you really want to understand chemistry, you need to be pretty good at this stuff too. All right, so that's the big ideas that we talked about. Get a conceptual feeling for what torque means, then remember that torque is I alpha, and know how to look up I for a different shape, or if it's just a point mass, use I equals mr squared. We did rotational kinetic energy, 1/2 I omega squared. Remember conservation of energy. We also did conservation of momentum, L equals I omega. For all these equations, you can do the same translation we did before. X becomes theta, V becomes omega, A becomes alpha, and we've got a few more to throw in. So to help you out, I made a little cheat sheet. You might want to pause or save this or screenshot this picture or print out later on if you want. The ideas here are just the same as we've done before, just in fancy letters. So let's take a look at this for a little bit. For position, X becomes theta, and we can relate them with S equals R theta for an arc length around a circle. For my velocity, V was X over T, so now it's omega is theta over T. And I can relate linear velocity to angular velocity with V equals R omega. Remember, meters per second equals meters per second. All right, same thing with A. Today we talked about my mass becomes I. The relationship is I equals the sum of mr squared. My force becomes torque, and the relationship is torque is force distance sine theta. My kinetic energy becomes 1/2 I omega squared. My work becomes W is tau theta. My momentum is L equals I omega. Same idea, not so bad to use. All right, that is it for rotation. Thanks for making it to the very end. I hope this helped. Have a great day.